this video, let's explore another method for solving a system of linear equations called Cramer's rule. Cramer's rule takes advantage of determinants and uses them to solve a system of linear equations. And it can be done for any number of equations, any variables. So in many ways, this will actually wind up being easier when we have very large systems. For just two equations, two variables, this is not necessarily so useful, but when we deal with 3 or 4 or 5, this certainly becomes more useful. All right, so let's just go through an example here. I think that's the easiest way to learn this. First, let's write this as an augmented matrix, which we've dealt with before already. So we're just going to write the coefficients in front of x and y and the solutions. So the coefficient on x is 1, coefficient on y is -3, and then the solution would be 6. I'm just going to make a line indicating everything after this is the solutions. Next row would be -4, 27, -19. And just to be very clear here, this first column are the x's, the second column is the y's, and the right-hand side here are the right-hand side of our equations. Basically, I don't see solutions. They're not really solutions for x and y, but they are what each of the equations are equal to. All right, so the way the technique works is we're going to find the determinant of the coefficient matrix. So just the matrix, just this one, just the one on the left here. So we want to find the determinant of 1, -3, -4, 27. Okay, so doing that very quickly here. Remember, 2 by 2 determinants are pretty easy to find. You just go down the diagonal and then do the subtract the other diagonal. Right, and if we do this, we get 27 minus, well, -4 times -3 is a positive, so -12 equals 15. All right, the next we're going to find d subscript x, which is the determinant of the coefficient matrix, where instead of all the coefficients on x, they're replaced with the right side of the equation. So we're going to take, instead of looking at the x's over here, we're going to replace that first column with 6 and 19. So let's do that. So instead of 1, we're going to write a 6. Instead of -4, we're going to write -19. We're just taking the x coefficients and replacing them with the right-hand side. We do nothing with the y's. Y is going to stay exactly the same as before. Now let's find the determinant of this. So let's see. 27 times 6 is 162. I guess that seems right. And then subtract 19 times 3 gives me 57. Subtract these two numbers and I get positive 105. Our last one, dy is going to be done pretty much the same way. But this time we're taking our solutions and replacing the y column with that. So starting with my original coefficient matrix, the x's are going to be untouched because that's not what we're solving for. The coefficients on y are going to be replaced with the, I don't want to say solutions or answers, but what these equations are equal to on the right. So it's 6, -19. And then find the determinant of this. So 1 times -19 is -19. Then subtract the product of -4 and 6 gives you -24 there. And so that would be, let's see, -19 plus 24 gives you just positive 5. All right, we're pretty close to the answer at this point. It doesn't seem like we've gotten anywhere, but here's the cool thing. Our solutions are just going to be this. X is going to be the ratio of dx over d, and y is going to be the ratio of just dy over d. So to solve for x, we're just going to take our dx, which is 105, and divide it by d, which is 15, which means x is 105 divided by 15, which is 7. Then y is going to be dy, which is 5, over d, which is 15. So y is just 1/3. And that's Cramer's rule. Of course, we want to write the answers in ordered pair, x first, then y. So it would be 7, 1/3. But that's it. In the next video, we'll do an example with a where there's 3 equations, 3 variables, but really this technique can be used for any number of equations, any variables, as long as you have just as many equations as you have variables. The only really quick word of warning is that at any point you have a determinant, the D of 0, that means that this is not going to be a valid way of solving equations. So this method does not always work, but as long as the original determinant of the coefficient matrix is non-zero, it will work.